Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. Today I'm going to talk about models, and specifically models with regard to epistemology, that is, the study of knowledge, and in particular there, scientific models. They're both interesting, as well as there are a number of misconceptions about them. So I'm going to talk first briefly about what they are, and then I'm going to talk about the various misconceptions that exist about scientific models, where people go wrong with these things. So, I actually have notes this time, because the first time I tried this, I rambled on for more than half an hour. It's a kind of complicated subject, so I'll be sticking to a sensible way of going through. Alright, so the first thing is, what is a model, just in general? Well, a model is anything which represents another thing, where there's some relationship in the thing which is true of the thing it represents. So consider model trains, which are a type of model. Well, what do they represent? They have a relationship of the exterior, basically dimensions, sizes, and so on, often colors as well. Where in a model train, you try to make the thing look as much as possible from the outside, like the original, and you do it by making sure that all of the relationships, like if the wheel is this big and the window is that big, then, however much bigger the real wheel is, the real window is exactly that much bigger too, and in the right places. That's a model. We're all familiar with that. So, now, the thing to remember, of course, is that models only partially correspond to the real thing. There will inevitably be differences between the two of them. That's what makes it a model and not one of the real things. So, for example, in model railroads, they're smaller. In another thing, they almost invariably don't use the same propulsion mechanism. So when you have a model railroad of a steam engines don't shrink down, and they'd be inconvenient even if they did. So you don't put a steam engine in, you put in like a electric motor into your thing. So that doesn't correspond. But the fact that you have, wheels that push the thing does, if you are really accurate, you do the drive wheel. But the exterior dimensions in any event do, and you can get the speed down and so on. So things will correspond and things won't. Nature of models. Now, of the various kinds of models, one type is a mental model. What is a mental model? Well, that's actually pretty straightforward. It's just a model that doesn't have any physical thing within the model. It exists entirely within your mind as an idea. So, the most famous kind of mental model is the scientific model. And what is a scientific model? Well, it's literally just a mental model about a restricted set of subjects. So you might have a mental model of, say, dating. How it works. What is the male supposed to do? What is the female supposed to do? That is a mental model. It's not, however, a scientific mental model because it's just on the wrong subject. Now, on the other hand, if it were about populations of insects or about electricity or what have you, then it could be a scientific model, or would be, in fact, a scientific model, because it's about the subjects that science is studying. So, something just worth bringing up is why those particular subjects? Why is science constrained to certain subjects and not others? Why is it not scientific when you talk about what makes for good jazz or how to go about dating or what have you? Well, the base, we'll get into it more, but the basic way in which these scientific subjects were picked is more or less that they are amenable to making mental models of the sort that people want to do in science. So the scientific subjects are more or less those for which doing this sort of thing actually works. It's just you look in amongst reality and then figure out, I've got a hammer, which thing around here is a nail? That's basically the approach. And it's a good approach. Like, if you've got a hammer, you really should figure out what's a nail and what isn't a nail and only hammer the nails. It's a good idea. Okay. So now, the next thing is, how do you know that the model actually corresponds to reality? With the model trains, it's really simple. You look at the small train, you look at the big train, and well, okay, they look alike. So they correspond in that way. And even more so, if you want to be more precise, you take measurements on the one, you take measurements on the other, and you make sure that everything has the same, integer multiple, or whatever multiple you want. Use floating point numbers, I suppose. From the small thing to the big thing, that every size on the small thing, of course, is something times that gives you that exact measurement on the big thing. Pretty straightforward. Well, how do you do this with scientific models? Well, basically, this is where you come to testing. And what is testing? in a scientific sense, that is basically just looking at the model, and then you have some things and you know that are related to other things within your model, and you go and look at reality and see if they are in fact related in that way as described in the model. Okay, but that's kind of general. How do you do that more specifically? Well, this is where you get to measuring. You do this by things that are measurable. Now, in the example that I had given of the model train, you do this by measuring distances. You measure several distances and they all correspond in the same way. If something's twice as big in the model as twice as big in the real thing, there you go, your model works. What this relies on is measuring. Measuring is something where any two people can come up with the same measurement by measuring the thing. That's sort of the main thing that makes a measurement a measurement. So when we take a yardstick and measure something in yards, if we do it right, we come up with the same measure. We come up with the same number of yards in the thing. If we weigh it, we came up with the same number of pounds, and so on. You can count things. It's measurement in general tends to be some form of counting, really. But in any event, you count things, and well, there you go. Now, that is the general scientific thing. What you tend to see a lot of, and especially in things like physics and somewhat in chemistry, and so some of the really, in a sense, the most glorious of the sciences, are mathematical models. Now, mathematical models are models that relate things mathematically, because you can have a model that relates things more generally, like behaviorally. You can have a behavioral model where if this happens, then that happens. If this other thing happens, then this other thing happens, and you can experiment around. Anyone's ever played the game of life? Not the board game. What do you call it? It's a game where you have all these individual, like the board is essentially done in cells, and then if there are two things next to each other, they die off but create other things, then you get patterns off of it. That's also a model of population behaviors or something. That's not very that's not very common though, and those things are very hard to test. Mathematical models, by contrast, are models that use mathematics, and basically this means equations. Now, to give you just a simple example, one of the classic mathematical models within physics that we've all heard of is force is equal to mass times acceleration. That's a mathematical model. It's an equation, and it's a model. That is to say, it relates several things that are related in the real world, we assume, and then describes this relationship in a nice simplified form that's easier to think about. And another way of putting this, because F equals ma is a very sort of abstract way of dealing with it. You need to go through a lot of training in order for this abstract thing to actually seem real, is just to say that force, mass, and acceleration are linearly related. If you double if you double force, you either have to double mass or double the acceleration. If you double the mass and keep the other, and keep acceleration constant, you double the force, and so on. That's what it's describing. It's describing those relationships. They're symbols being used for it, but that's what those symbols mean. So how do you test a mathematical model like this? Well, this is exactly where you do measurements. You take measurements. You measure the force, you measure the mass, you measure the acceleration, and see if the force is equal to the mass times the acceleration. Now, this brings us to the subject of predictions. What I just described is making a prediction in the scientific sense. You've got force is equal to mass times acceleration. What that means is it predicts that if you measure the force, mass, and acceleration, the force will equal the mass times the acceleration. That is basically all a prediction means. It's almost somewhat unfortunate that the word prediction got used, because prediction tends to mean like describing what's going to happen in the future of a complex system. That's not what prediction in the scientific sense means. It does not mean what goes on in a complex system at all. In fact, in general, the way you do it is that you make a very, very controlled circumstance as simple as you possibly can, so that there is nothing but what is in the model. And then you see whether or not all of the pieces relate to each other according to the way that they are in the model. Another way of looking at this is that if you, for anything, like in this equation that has three variables in it, it's describing three things in the real world: force, mass, and acceleration. Any two of those predicts the third. So that if you take these three measurements, and you have to measure all three of them, you can take any two of them and see will this plug them into this formula, solve for the missing one, and is that what you actually measured? Now, there's a detail in this because it will never be exactly what you actually measured, because there's always going to be measurement error. We don't have the ability to measure things with perfect accuracy. But within the realm, you have a sense of how accurately you can measure, and there are ways essentially of quantifying how accurately you can measure. These things themselves there's sort of a problem of infinite regress. That when you quantify exactly how accurately you can measure something, you have to have done that by way of a measurement, which itself would require a certain amount of qualifying how accurately you can measure that. So there's an infinite regress, but we tend to ignore it because it diminishes. And so the nature of it is just that you quantify essentially how close you are, and then what you describe when the relationships come out to within the errors of your ability to measure it, then as far as you can tell, this is accurate. This does accurately describe it. And this is why, incidentally, you'll see a lot of people who essentially, in some sense or other, retreat to engineering. Because in engineering, you don't care beyond that. You only want an approximate number anyway, because you're then going to, multiply by very often 5. How thick does the steel girder need to be? And then, to bear this weight. Now, how thick does the steel girder need to be to bear 5 times that much weight? And as long as the one is well outside of your error measurement from the other, you then just make it so much thicker than you need to, and presto, you're not going to have the thing buckle on you in the normal human course of events. Doesn't work epistemologically that way. It's fine for engineering. For epistemology, that is to say for knowledge, whether or not you know something, whether or not you know this model actually corresponds to reality, you cannot say that the model does. You can't say that the prediction has really been verified in this sense. All you can say is that it has been verified to within your ability to measure. This will come up in a bit. Now, something else to note is that when we talked about what is science in investigative subjects, in general, science is, to qualify what we said before and make it a little more precise, science focuses on that which is measurable. That is to say, it limits itself to those subjects which are measurable, which can be quantified in some way by counting, whether it's, counting individual things or measuring in the sense of, and because measuring is still counting, measuring distances, measuring weights, measuring velocities, measuring time. One of those things, science basically limits itself to measuring those things. Anything which can be measured in terms of any of the basic things we can measure is, in general, a subject for science because you can then carry out this method that has been worked out. And I should say, this is in theory. You will find plenty of things which don't do this, which claim to be a science, and for which there's lots of debate as to whether or not they're a science, with the people in it wearing the lab coats and getting the funding saying, of course we're a science, and people outside of it often looking at it and saying, yeah, but you're not actually measuring anything, you're not doing the scientific method in any recognizable sense. You've got models, but there's no way to actually test these models against reality to see if the correspondences in your model are real correspondences in reality. And then the other people say, yeah, but look at the lab coat, respect the lab coat. Anyway, I'm phrasing that in a slightly humorous way, but there are all sorts of fuzzy edges around this, where people don't adhere to this and claim to be a science and other people dispute it. But things that do rigorously adhere to this, in general, everyone will tend to agree is a science, because they can just simply point to all their measurements. The measurement, by the way, is the experimental branch of science. The constructing of the models is theoretical, like theoretical physics or theoretical chemistry. And then the actual carrying out of the experiments, that is to say, the doing of the measurements that are described in the formulas, that's the experimental side. Although the experimental side can also just be an exploration of what happens when you do this, and then this can give people ideas for the models. So it can feed back, and we'll talk about that in a little bit. And I just want to say there's a big benefit to focusing on measurements. It leaves out most of the world, but it does have a number of real benefits to it. One of the big ones being that it makes people focus in a practical sense on measuring things accurately, and that is very useful. And in fact, if you look at the history of science, you will find that to a great degree what was called the scientific revolution was not in fact that... I want to be careful in what I say. There was something that you can accurately describe as the scientific revolution, but it is overstated. A lot of what happened actually, when you look at the time period of the scientific revolution and drill down into the specifics of exactly what was going on, is that over time, people's ability to measure things had been getting more and more precise. And once this had gotten past a certain level of precision, people began to be able to this feeds back on itself. I'm sorry, let me back up one step. When you can measure precisely, it then enables you to make more precise measuring devices, which then allow you to measure that much more precisely. That is to say, the more accurately you can measure a distance, the more accurately you can make the next device which measures distances. The more accurately you can calibrate, you can calibrate time. The more accurately you can do that, the more accurately you can measure all of the pieces involved in the thing that measures time. The more accurately you can measure time, often the more accurately you can measure distances, and so on. And if you look actually in the late medieval period, prior to what's called the scientific revolution, you see some major breakthroughs, especially within timekeeping devices. In particular, the nature of clocks, for example. Which mechanical clocks had been developed, and they're some of the most precise things that anybody had yet made at that point. And technology had gotten to the point where they could make these very fine, high-precision things, which then allowed the high-precision measurement of time, because a mechanical clock measures time so much more accurately than, like, water flowing through something. And also more conveniently and easily, because all experiments have to be conducted by people. Another thing that was happening, too, which actually allowed a lot of astronomy, was the development of lenses for eyeglasses. And then once people were able to do that, they're able to take the same technology and then make them essentially a little bit bigger and a little bit, just variations on it roughly, and then be able to see great distances. And then you have the beginning of telescopes, which again are, some of the beginning of the scientific revolution. But it's not like people weren't, it's not like science happened and then people came up with telescopes. It's really much more the reverse, that the ability to measure precisely leads you into doing things that you had never tried to do before, because there would have been no point before, since you could never have measured precisely enough. So this focus on measurement is very useful in that it measures precisely. And if you look, just to finish that up in its utility, if you look at the way most science is carried out today, it tends to have a lot of focus on off-the-shelf parts which you can buy rather than construct. If you look 300 years ago, scientists often had to build their instruments. And so a lot of the carrying out of practical science was the building of instruments, whereas these days you find much more of people, a large enough number of people who want high-precision measuring devices that somebody just goes and makes them relative mass production, sells them relatively inexpensively, and then a lot of people can go use those for precise measurements of various sorts of things. So this has created an industry of hyper-precise measurement, which is all to the good, because the ability to measure precisely is very useful for lots and lots of things, practical as well as theoretical. Okay, so that's the description of scientific models. I want to move on now to misconceptions. So the first one is I just want to talk about that fact that science limits itself to the measurable, or at least things like physics and chemistry tend to limit themselves to the measurable. And this is, as I said, this is when all you have is a hammer, actually considering what is and what is not a nail, rather than just assuming that everything is a nail. Works out much better. But it doesn't mean that because hammering nails works really well with a hammer, that there's nothing else in the world, or that this is the best way to affix two things together. It's not. It depends very much on the particular circumstances. And bringing it from the analogy to what it's an analogy for, there are lots of kinds of knowledge, and most knowledge is not scientific. Most knowledge is not of things that you measure. Most of the time, we do not take measurements of anything we do in normal life. The number of measurements you actually take is probably less than a dozen within a day, and a lot of them are going to be timing food that you are cooking. So we don't use measurements by and large. We don't do that sort of thing, so that the scientific approach, while very useful within its field and for the things it can be good at, does not talk about most of life. There's a tendency that you will see because of certain developments in modern, with capital M, philosophy that basically deny the ability to have knowledge, that people will retreat to the scientific method as the next best thing because, like, hey, at least within here we get some reasonable confidence because of the nature of testing. And the answer is, well, yeah, if you have a terrible philosophy like modern philosophy that denies the existence of knowledge, I can see why this seems like the best thing that you have available, but just chuck the terrible philosophy that's very wrong, and stick with a, good philosophy. It'll work out a lot better. Admit that we actually have knowledge. Like I know that I'm actually holding a piece of paper right now. And, yes, you will find if you try to deny that, then yeah, everything goes bad. But that's just the results of a terrible philosophy, and not something about science actually being any sort of universal thing or the best hope of humanity for knowledge or anything like that. It's just within a terribly damaged, broken philosophy, you do get that result. Okay. Predictions. A common misconception that I have seen about predictions is roughly treating them as if they were prophecy. So, prophecy being, roughly speaking, the prediction of the outcome, that is the foretelling of the outcome of an incredibly complex system that nobody can measure, or simply that nobody can measure. That'll suffice for the moment. So, for example, very famous prophecy is the prophecy of Joseph to the Pharaoh, that there will be 7 years of plenty followed by 7 years of famine. So during those 7 years of plenty, build up large grain stores and store up as much food as we can during those 7 years, because it's going to have to last us the next 7 years after that. That is a prophecy in the sense of foretelling the future of a complex system that nobody can measure. Nobody can measure things like the amount of sunfall that's going to happen, the amount of rain that's going to fall, and so on. Those things are not measurable. Nobody can foretell the future of these things. And so therefore, someone who can tell you the future of these things, I mean, no one can tell you the future in the ordinary course of events. You hold a gun to someone's head and say, how much rainfall will there be 8 years from now? They're not going to give you a number that is perfectly accurate. Normal human beings, except by sheer luck. Now, that's a prediction, and this tells you that sort of prediction, the ability to predict the outcome of a complex system which nobody can even begin to measure. That tells you that the person who's making that prediction that turns out to be correct is in touch with something greater than humanity, something more than human, something greater than humanity, something greater than a human being can know this, possibly. And when it's shown that they do, something greater than humanity knows what is going to happen, can foresee the outcome of events, and is then in contact with a person who is able to do this thing that human beings can't do. That's why people want things like prophecies or miracles or what have you. For those who are claiming to be greater than human, prove that you're in touch with something greater than humanity then. Do one of the things humanity can't. And the two big things are things like miracles and things like predicting the future. Predictions in the scientific sense are not like that at all. They are not predictions of a complex system. They are, in fact, predictions of a system simplified as much as possible. As I said, the nature of earlier, the nature of scientific experimentation is you control every variable that isn't in your model and see if only the things in the model relate to each other that way. So the other thing is that they're not of the future in like a strict sense. It works perfectly well for a scientific prediction to be of things that already happened. So you can measure a collection of things, positions of planets and stuff at different times. And if your model is able to show from one time where, the relationship between the positions and velocities and stuff of all the stuff in the beginning, and then at another time, that is a verified prediction. It doesn't have to be in the future to show that the model is accurate. And I mean, just think about the nature of models is such that, like, if your model shows that these things will always be in a triangle, and then you measure and then you look and see, like, people who'd already measured the things, and they're always in a triangle, well, there you go. Like, it shows that the relationship in your model is accurate to reality. You don't need to wait and measure the things one more time if you have 10,000 measurements already. There's no need to do that. It's not relevant to the nature of these predictions. So that's why prediction is a very unfortunate term in this case, because it doesn't mean of the future. There are some high-profile cases in which predictions were of the future. The transit of Mercury is one that Newtonian mechanics did not accurately indicate the position where Mercury would come when we'd be able to see it again after it was in front of the sun and you just couldn't see the thing because the sun's too bright. And so, or maybe it was when it was behind the sun. I can't remember which of the two it is. Anyway, one of the two of them. You can, it would not accurately show you, the models did not accurately indicate where it would be. And the general relativity did. However, there really is no need whatsoever for that to have been, taking these positions and showing where it will be next. It would work just as well. It would show general relativity just as corresponding to reality to have done this with measurements someone had already taken. It just happened to have sort of the drama of, showing where it'll be, and then everyone waits on bated breath to see if it's actually there. But that's not inherent to the nature of a scientific prediction. Predicting older stuff is just fine. There is an asterisk on that, and that you do need it to be of things where you have a reason to believe that they're going to be the same each time. In complex systems, the fact that you can predict the past from the even previous past doesn't really show much of anything, because you've got no reason to believe. Well, it's not a controlled experiment. You've got no reason to believe that you've captured all the variables or have controlled everything. So the mere fact that it was able to predict one thing, one relationship, doesn't mean that it'll predict other relationships. But it works perfectly fine if you had, if you broke the past up into 1,000 segments and then predicted the second half from the first half, and you already had these measurements, that would be fine, because you're showing that the relationships involved apply more than once. It's only when you break history up into literally 2 segments and predict only one from the other, you may be capturing a relationship that only exists in this one data set. That's the relevant thing there. So to give a really, really simple example of how predictions are not, not of the future in a complex system, it would be a perfectly scientific prediction to have, the rotating Earth predicts that the sun will come up tomorrow. Bet your bottom dollar that tomorrow there'll be sun. Possibly through the clouds, but that is a perfectly valid scientific model. It is a prediction in the scientific sense that the sun will rise tomorrow. And when the sun rises tomorrow, woohoo, your model has been verified in this regard. No one's going to really care, because everyone, kind of already knows the sun is going to come up tomorrow. That's something that all of humanity is more or less agreed upon anyway. But that is a prediction in the scientific sense. And if you look at actual, verified scientific predictions, they are very frequently of this nature. They are things that, they're quantifications of relationships where nobody didn't, this isn't a surprise. This isn't the outcome of a complex thing. This isn't predicting what the next lottery numbers are going to be. This isn't going to, this isn't predicting who's going to be the president of the United States in 2235, and then, sealing it in an envelope and leaving it around for a few hundred years. This isn't that sort of thing. Things that happen all the time are perfectly valid to be predictions of a model. It's a confusion of terminology to think of the two as being like each other, or that the verified predictions in the scientific sense is analogous to someone who's able to foretell the future years down the line. Okay, another very important thing is that models are intrinsically incomplete. I mentioned this earlier, but they always leave things out. Mathematical models in particular are intrinsically incomplete because there are always going to be infinitely many models that have this particular model as sort of a sub-condition. So, for example, there could always be, force equals mass times acceleration. Well, that is, in fact, an incomplete model. It's actually like the summation of forces is equal to mass times acceleration. Because, you can do something like, I'm applying so much force on this paper, it's got a certain mass, it should be accelerating. It's not. It's holding still. Well, does that disprove the model? No, because really it disproves a very trivial interpretation of the model, depending on what you're going to consider force. But it's really the summation of forces, because there's a force of gravity pushing down and there's a force of me pushing up. The summation of forces goes to 0, at least while I'm holding the paper steady. And so you get no acceleration as a result. But so there, you get a summation of forces. There are Newtonian mechanics and relativity is one of the best examples, because there are various terms in the general relativity equations that, if you work out under very specific circumstances, ends up being very close to the Newtonian mechanics. And so, for a long time within the measurement era of Newtonian mechanics, it's various things like a high gravity, very, very high gravity, high mass situation is where those other terms in the equations become so big that the equations don't work out the same at all. Like in the case of the sun and Mercury, that was a case where those extra terms actually mattered. But the thing is, there are infinitely many other equations that will have, as a degenerate case, that thing. The thing that you do know, the thing that you actually have measured. So the mere fact that your model has been measured against reality only tells you something about the conditions in which you have measured it. So that you can say, yes, in this particular, if you measure something, you measure the things described by the model, and in this experimental condition, it works out that the formula is correct. It does relate these things properly. You can say that the formula has been verified in that circumstance and in that circumstance only. You cannot rule out that in other circumstances there are things that you happen to have controlled for in your experiment that are not always controlled for and will affect things. So, okay. That is, by the way, actually the point of testing. Testing, its purpose is to eliminate everything that is not in the model. That's your goal in testing. It's not always achievable. For example, you might accidentally do this. It's a really good example that Richard Feynman gave in his book, Surely You're Joking, Mr. Feynman, about, say you're trying to look at the way that a pendulum precesses, over time. If you're not familiar, weight on a string that swings back and forth, eventually it changes direction. Throughout the day. It has to do with the rotation of the Earth. And you could do this experiment, and if you don't realize, just for the sake of argument, you don't realize that whether you're on the northern hemisphere or the southern hemisphere is significant, you can have the most isolated laboratory in the world built within, deep within the Earth inside of a fortified bunker and so on, testing this, and it looks like the most, you've got a perfect vacuum and everything else, you've got the most controlled circumstances you possibly can, and it turns out that you didn't think that being on the northern hemisphere was significant, and it turns out that it is. That if you conduct that exact same experiment in a mirror lab on the other hemisphere of the Earth, you'll get actually the opposite result. Which latitude you're at, and so on. Like it's actually, I'm sorry, the latitude doesn't matter until you hit the equator. But anyway, what do you call it? The point being, you think you controlled it, but you didn't necessarily. That your model of how the pendulum proceeds has a variable in it, which hemisphere of the Earth that you're on, that you simply didn't take into account. So the mere fact that you think you controlled everything, that your model verified in a lab, doesn't mean that you were not simply accidentally lucky and there were variables that are highly relevant that you simply didn't measure. There's absolutely no way to know this other than varying your circumstances. But there is, this is the thing, you'll find lots of people who will then angrily scream at you that you have to assume that there's nothing else until it's shown that there is, but you don't. That's not an actual principle of anything. That's not how knowledge works. That's not how science works. You don't assume that there is nothing significant until, someone proves it to you otherwise. It's, more properly called humility, that you should be aware of what it is you don't know. No. Okay, so the more general point to that is that a model corresponding to reality under test conditions doesn't really mean anything outside of those test conditions. You can assume that it does, but, and this is where a lot of people go wrong too, in not knowing the actual specifics of scientific things. That just to give a concrete example of the sort of thing that I'm talking about, most of the experiments that go on with electrons tend to be in high energy environments. Because they're so small, we can't measure individual ones in low energies. We're so big relative to them that anything we do imparts so much energy, and we need so much energy just to be able to see some effect from it, that we can't really do, genuinely low energy single electron experiments. It's not really within the realm of possibility. So what we do is we do high energy, large number electron experiments. I'm broad brush here. I'm not saying that nothing's ever been done. But as a general rule, it's things like particle colliders. It's things like cyclotrons. Stuff, other things where you are highly energizing these things. And then like flinging them at stuff and various stuff, shooting them and seeing at the angles at which they deflect and things of that sort of nature. And just to give an analogy, if you were to conduct an experiment where you throw people off a building at high speed or put them into a catapult and launch human beings, well, they will tend to have a pretty predictable statistical pattern. It won't be use the catapult or trebuchet, because trebuchets are even cooler than catapults. Put people in a trebuchet and launch them. there'll be a minor dependence on how they angle themselves through the wind and so on. So they're not going to land exactly on the target if you get a good 1,000 yards. There'll be a little bit of variation in there, but you'll be able to predict pretty accurately how they go when launched out of a trebuchet. That tells you nothing whatsoever about how, if you let them walk around, how a human being is going to walk, how they're going to walk when they're in an open field, how they're going to walk when they're in a sports stadium, how they're going to walk when they're in a school building, how they're going to walk when they're in someplace else. Your experiments in the trebuchet, no matter how statistically reliable to this controlled environment of launching people in high velocities in a trebuchet, doesn't tell you anything about how human beings behave when they're not in this trebuchet being launched at these really high velocities that overcome their ability, well, even more so, in sort of relatively empty space. In the same way, the experiments that go on with electrons tend to be in very high energy environments where we're directly manipulating the things, and very little of them have to do with watching electrons in their native environments, because we basically can't. Moreover, the ability we have to watch an electron simply is so high energy relative to the electron that it will tend to interfere with the electron and move the thing around. It's a little bit like what happens if you're trying to see what a person's doing, and the best you can do is shove them to see whether or not they're there, and you walk around, shoving until you actually feel someone aha, there was a person there. That's one of the problems we have with watching electrons. We can't really do it in, loosely speaking, their native environment. All the more so, and this is just an interesting example, sort of, I think is a good final example of it. Nobody has ever conducted a scientific experiment of an electron that is part of a human brain taking part in the process of being a thought. Nobody's ever conducted a physics experiment on an electron doing that. And it's intrinsically impossible to do that, because the moment you were to be interacting with it so as to be able to measure it, you would be interfering with its normal course of events and taking it out of being part of that thought in the way that it would have been doing had you left it alone. It is, it's a little bit like the, how you can't do a double-blind, you can't do double-blind talk therapy experiments, for example, because the person to whom you're talking has to know what you're saying in order for it to even possibly be relevant. And the moment they know what it is, it's not a blind experiment. So it's intrinsically impossible to perform a double-blind experiment. Just is. It's one of those unfortunate things, it's not measurable in this fashion. In the same way, what electrons do in low energy environments when they're part of some natural process, and not just necessarily thinking, photosynthesis or other stuff, how do they behave there? We have no idea. No one's ever run an experiment as part of this. It's actually intrinsically impossible to run that sort of measured experiment. It's part of why no one has. It'd be very, very difficult to actually cram, the relevant machinery into a human brain without killing the person anyway, which is an even more practical reason why no one's even considered trying it. But no one has. So what happens? How do electrons behave outside of that controlled laboratory environment where you're firing them at high energy and so on? No one actually knows. Now, people will yell and scream at you in angry ways that it's got to be exactly the same way as in that controlled experiment, or otherwise, go and get, prove that it's different and get your Nobel Peace Prize or something. But that's ironically, that's what they would call the burden of proof fallacy, that they're saying the burden of proof is on you to prove this thing that to prove the contrary of what they have no evidence for. Since they have no evidence for how an electron behaves in there, they have in general, what you'll find, and I'm not going to go down this path in detail, but in general what they have is a faith that the world behaves according to simple mechanistic rules that are context independent for context like a human being or living things or so on, generally that are independent of the context of intentionality, more or less. And so they have this faith that this is the case. They cannot prove that this is the case because it would require observations they intrinsically can't make. And so they get very, very angry at you when you point this out and then tell you that, the burden of proof is on you in order to disprove their faith that the world is as mechanistic as they think it is. But yeah, in truth, they simply don't know, and we don't either, how electrons behave as part of thoughts in a human brain. And it's outside the scientific method to find out how they behave there. That's not what science is about. Science is not about everything. Science is about measuring what is measurable and seeing how things behave where it is measurable. And even the tie into engineering, nobody engineers things that depend on how electrons behave in this particular way. So the engineers don't care either. They don't really need to know any of this, so they don't care either. So nobody actually is trying to investigate how that works. This is simply, actually, properly speaking, an area of ignorance. This is outside of what science investigates. It's outside of what engineering deals with. And yeah, that's a good illustration, I think, of the limits of the scientific method. And it's the nature of it that the scientific method is very powerful when it constrains itself to being able to use certain tools. And when it can't use those tools, it's just not the thing to be using here, not the thing to consider. And it's not a knock against science in any way, shape, or form to note that. It's simply noting that the thing is intrinsically limiting itself to its competencies. And when you're outside of that, you should stop asking it questions that it's not equipped to answer. So anyway, I'm sorry, I just need to throw out this qualification and then we'll be done. And the qualification is that doesn't mean that go and believe anything that you like. That means that since you're outside of where this works, you need to use other means of knowledge. And that's where it'd be really good to have a philosophy that doesn't entirely rule out all other forms of knowledge, because otherwise you're just completely stuck for everything that matters. So, yeah, I don't mean go and believe anything you want at that point, but rather you have to use your brain and think in other ways besides this one, because really you should have more tools in your tool belt than just a hammer. Until next time, may you hit everything you aim at.